Hello everyone, welcome to OpenCV practical course. This is Sujay, your instructor for the OpenCV practical course, and in this video we will be starting off with the second project in OpenCV, which is the hand detection application. We saw in the previous videos that we completed the motion detection application in which we were detecting any motion given in a video. Now we will extend that idea of motion detection in order to detect hand in a video. So in the previous project, what we did was we took the background of a video and modeled how a background of the video looks like, and if the frame changes significantly from how the background looks like, then we were detecting it as motion. So similarly, even in this hand detection, let us see how we will be using similar principles of background modeling and thresholding in order to find out whether a hand or a gesture is being performed in the video. So in the next video, I will be going over some introductory concepts that are required for building a hand detection application. Hello everyone, welcome to UpDegree. So this is Sujay, your instructor for the OpenCV practical course. In this video, we will be going over some basic concepts that we will be requiring for building a hand recognition project. So in the previous video, we saw a brief introduction to what hand recognition is, and in the previous video, we also built a basic motion detection application. So in this video, let me go through some of the basic concepts that are required for building a hand recognition software. So in this video, we will be going over some of the brief theory behind how a hand recognition project is built. So after this project, you will know how to approach a computer vision problem step by step. You will also know about background subtraction and motion detection, which we have already used and built a motion detection application in the previous project. Then we will also learn about what is thresholding, what are contours, so what is the difference between them and how to build a contour and how to threshold an image. Then we will also learn how to implement the above concepts in code using OpenCV and Python. After that, we will also build an application which will segment hand region effectively from a real-time video sequence. Hand gesture recognition is a very cool project to start for a computer vision enthusiast, as it involves an intuitive step-by-step procedure which could easily be understood, so that you can go on to build more complex stuff on top of these concepts. So like I said before in the previous project, there are some prerequisites that we will need in order to go ahead. So I am assuming that you are already familiar with the basics of Python, NumPy and OpenCV, as they are the prerequisites for this tutorial. If you want to quickly understand core concepts in Python and NumPy, you can check out the basic documentations that are available online. In addition to these, you should also be familiar with image basics such as what are pixels, what is an image dimension, what is a video, what are frames of a video, frames per second, etc. and some basic operations with images such as thresholding and segmentation. Do not worry if you do not have an in-depth understanding about what all of these mean. If you know in a brief high-level view what these words mean, it is sufficient because we will be learning about them in this video. So coming to the introduction part, so gesture recognition has been a very interesting problem in computer vision community for a long time. This is particularly due to the fact that segmentation of foreground object from a cluttered background is a challenging problem in real time. The most obvious reason is because of the semantic gap involved when a human looks at an image and a computer looking at the same image. Humans can easily figure out what is in an image, but for a computer, images are just three-dimensional matrices. So for a computer, they are just RGB values of each pixel. If you are aware of what pixels and what RGB values are, you must already know that each image consists of pixels, which are individual dots in an image that make up an image. And each of these dots is represented by three values, that is red, green and blue, or RGB values. Now the values of these RGB is what determines its color. Therefore, for a computer, images are just three-dimensional matrices. It is because of this that computer vision problems remain a challenge. So another important challenge is the semantic segmentation problem, where the objective is to find different regions in an image and tag its corresponding labels. In a case of an image where there is a person, we will have to label which part of the image constitutes the sky and which part of the image constitutes person, which part of the image constitutes a tree, and which part of the image constitutes grass. A quick Google search will give you the necessary links to learn more about these research topics. As this is a very difficult problem to solve, we will restrict our focus to nicely segment one foreground object from a live video sequence, which we are going to do in this project. So now, what exactly is the problem that we are trying to solve? So I will go ahead and let you know what is the problem statement. So the problem statement is that we are going to recognize hand gestures from a video sequence. To recognize these gestures from a live video sequence, we first need to take out the hand region alone, removing all the unwanted portions in the video sequence. After segmenting the hand region, we then count the fingers shown in the video sequence as a gesture. Thus, the entire problem could be solved using two simple steps. Find and segment the hand region from the video sequence, and 2. Draw a contour around the hand to segment the hand region in the video sequence. How are we going to achieve this? To understand hand and gesture recognition in depth, we have created this video for you to understand how to do this in a practical manner. So in the next video, we will start with the first part that we will need for this tutorial. So let's get started and see you in the next video. Hello everyone and welcome to UpDegree. This is Sujay, your instructor for the Practical OpenCV course. In this video, we will be going over the first part of building the hand recognition project, that is the second project in this video series. So in the previous video, we saw some of the prerequisites and the introduction that we had to go through before coming here. So let's get started. So the first part that we will need to do is we will need to segment the hand region. The first step in hand gesture recognition is obviously to find the hand region by eliminating all the other unwanted portions in the video sequence. This might seem to be frightening at first, but don't worry. It is a lot easier using Python and OpenCV. Now, I hope you all understand that a video sequence is just a collection of frames or a collection of images that run with respect to time. Before getting into further details, let us understand how could we possibly figure out the hand region. So the first part is the background subtraction. If you can see the slide, you can see that the first question that we will be answering is how to do background subtraction. So coming to this part about how to do background subtraction, first we need an efficient method to separate foreground from background. To do this, we use the concept of running averages. We make our system to look over a particular scene for 30 frames. During this period, we compute the running average over the current frame and the previous frame. By doing this, we essentially tell our system that the video sequence that you looked at, that is the running average of those 30 frames, is the background. After figuring out the background, we bring in our hand and make the system understand that our hand is a new entry into the background, which means that it becomes the foreground object. But how are we going to take out this foreground alone? The answer is background subtraction. So for all of those who followed the previous project, that is the motion detection application that we built in the previous video, then this must already be familiar to you guys. So even in the previous video, during the motion detection, we modeled the background by telling the computer that the first couple of frames is what a background looks like, and any changes to this background frame is the foreground. Now how did we do that? We recorded the video for the initial frames and we said this is how the background looks like. And after that, whenever motion was detected in that video, that means the background changed or a new object entered into the video, we detected it as the foreground. that means that the motion has been detected. So in the previous project, we just saw that as soon as the motion was detected, we put out an alert saying that motion was detected. But in this project, along with identifying when the motion has been detected, we also have to draw a bounding box and find out whether the foreground object that actually came out was the hand or was it just a random motion. So that is the challenge that we will be facing in this project. So like I explained, so background subtraction is done by taking an efficient method to separate foreground from background. So the running averages is something that we already established in the previous project, where we did not exactly a running average, we just took absolute differentiation or absolute difference between the background image and the current image. That is the frame of the video. So only if this absolute difference is greater than a threshold, we detected it as a motion. But in this case, we will be taking the running averages of 30 seconds. So what is running average? We will be calculating averages of the RGB values of the window over the frame. So after figuring out the background model using running averages, we use the current frame which holds the foreground object, which is a hand in our case, in addition to the background. We calculate the absolute difference between the background model, which will get updated over time, and the current frame, which has our hand, to obtain a difference image that holds the newly added foreground image, which is our hand. This is what background subtraction is all about. So coming to the second topic, that is the motion detection. So as you can see in the slide, the second topic that we will be learning and doing is the motion detection part. To detect the hand region from this difference image, we need to threshold the difference image so that only our hand region becomes visible, and all the other unwanted regions are painted as black. This is what motion detection is all about. So you might be asking, what exactly is thresholding? So thresholding is the assignment of pixel intensities to zeros and ones based on a particular threshold level, so that our object of interest alone is captured from an image and everything else is marked with a 0. So you can consider this as kind of like a masking. So we will be masking all the pixels of the image that we are not interested with a 0, that means pitch black, and all the other regions that we are actually interested with white. So that is motion detection and thresholding. As you can see, the next topic that we will be covering is called as the contour extraction. So after thresholding the different images, we find contours in the resulting image. So the contour with the largest area is assumed to be our hand. So to summarize, what are the steps that we need to take is that background subtraction, motion detection and thresholding, and contour extraction. So we are already familiar with background subtraction and motion detection from the previous project. But this contour extraction is something that is new for us. So in the next video, I will be covering what exactly is contour extraction, and we will go from there. Hello everyone and welcome to UpDegree. This is Sujay, your instructor for the OpenCV practical course. In the previous video, we've learned about motion detection and background subtraction that we need to do in order to do hand gesture recognition. And we came to the third point of how to do contour extraction. So in this video, we will be going over some of the basic theories that we need to understand in order to do contour extraction. So what are contours actually? So contours in simply as a curve joining all the continuous points along the boundary having same color or intensity. The contours are a useful tool for shape analysis in object detection and recognition. In our case, since we are trying to build an object detection algorithm and the object being the hand, contours are very important for us to find out whether we are actually detecting a hand. So for better accuracy, before finding contours, we need to apply threshold or candidate detection. So in our case, we are already applying threshold. In OpenCV, finding contours is like finding white objects in black backgrounds. So we have to remember that the object background should be white and foreground should be white. So like I said in the previous video, When we did thresholding, we applied black or 0 on the background and 1 or white for foreground. So now what exactly is contours? So to do contour detection, OpenCV provides a function called as find contours, which intends to find contours. Of course, some treatment should be applied to the picture in order to get good contour detection. So we will be first using threshold to subtract background from foreground. Then we should apply find contours function to find contours and print them in the color image. So there are some important points that we need to keep in mind while extracting contours. The image should first be converted into grayscale. A simple threshold must be applied. We should mask the background. The find contour functions is called with a list of contours, and these retrieved contours are applied colored. So now that we have understood what contours extraction is, let us go back and summarize what are the steps that we needed to follow in order to get the contours. So the first is the background subtraction, the second is the motion detection, and the third is the contour extraction. So now that we are thorough with the theory behind how to do the hand detection, in the next video I will be diving deep into code to explain how to do the code themselves. Hello everyone and welcome to UpDegree. This is Sujay, your instructor for the OpenCV practical course. In this video, we will be going over the code of how to implement the hand detection algorithm and to explain each and every step that we will be taking in the code. So as you can see from the screen, we will start off with this Python script which can be used to analyze hand gestures by contour detection and convex hull of palm region using OpenCV, a library used for computer vision processes. So first, we import all the essential packages to work with and initialize the model. So in case you don't have these packages installed in your computer, you should follow the previous videos where I have explained how to install these packages. So coming to the next part, here we are opening a video capture channel to the webcam. So here cap will hold the pointer to the webcam, and we are starting a loop here where we are saying that as long as the video camera is open, we need to execute the code that is there inside this loop. So coming to the first part, we will read the frame that is given by the webcam. So this frame will be stored in this image variable. So next we take a sub screen or sub window on the screen. So we will not be detecting hand from the entire screen or the entire video. So we will define a sub screen that is 300, 300 and 100, 100. So this is a rectangle inside which if a hand appears, we will detect it. And then we will crop the image to that rectangle. And then we convert this image into grayscale. So why are we converting this into grayscale? So our ROI, or the region of interest, is the hand region. So we capture the images of the hand and convert them to grayscale. Now you might be asking the question, why are we converting it to a grayscale? So the answer to that question is that we convert an image from RGB to grayscale and then to binary in order to find the ROI, that is the region of interest. So the portion of the image that we are further interested for image processing. By doing this, our decision becomes binary. Yes, the pixel is of interest, or no, the pixel is not of interest. As you might have already seen if you have gone through my previous video, that this is very important for contour extraction. So for contour extraction, we need to have a black and white image in which the contours or the object of the contours that we are interested in extracting should be of white and everything else should be black. So if we have an RGB image, it becomes very difficult for us to get this binary image. Therefore, we convert it into a grayscale image so that it becomes very easy for us to do this decision of subtracting the foreground from the background. So that is what we are doing here in the conversion to grayscale. And then we will be blurring the image. So here I've used the Gaussian blurring on the original image. So why do we blur this image? So like I said, even two identical images might have different thresholding or different changes in the absolute difference. So like we saw in the previous project, that is motion detection, we saw that if we do not apply blurring, then the absolute difference between two subsequent images, even though they look identical, can be very high. Therefore, we apply Gaussian blurring on the original image. We blur the image for smoothing and to reduce noise and details from the image. We are not interested in the details of the image, but in the shape of the object to track. By blurring, we create smooth transition from one color to another and reduce the edge content. We use thresholding for image segmentation to create binary images from grayscale images. So as it might be apparent to you by now why we are using blurring. So if we don't use blur, then in the image there will be sharp edges. So for example, if you take the image of a hand, and there will be a sharp edge between the hand itself and its background. Now even if this hand moves by 1 pixel to the left or to the right, then we will lose all the information regarding how that hand looks like. Therefore, we need to eliminate this edge effect where there are sharp edges between the objects, so that we can have a smooth transition between the edge and the surrounding images. So if we do this, we will be able to consistently extract the shape of the object instead of worrying about the exact edge and the pixel at which that edge occurs. So that is why we do the Gaussian blurring. Then we do the thresholding. So what is this thresholding? In very basic terms, thresholding is like a low pass filter by allowing only particular color ranges to be highlighted as white, while the other colors are suppressed by showing them as black. So I have used Otsu's binarization method. In this method, OpenCV automatically calculates and approximates the threshold value of a bimodal image from its image histogram. But for optimal results, we will need a clear background in front of the webcam, which sometimes may not be possible. So like we discussed in the theory part of this project, we saw that we need to do thresholding in order to mask all the background images with black and all the foreground images with white. So how do we do this thresholding? OpenCV gives us a very easy interface to do thresholding using something called as Otsu's binarization. So what exactly is Otsu's binarization? So in Otsu's binarization, we assume that the image consists mainly of two colors. One is the background color and the other is the foreground color. So what Otsu's binarization does is it models the background color and the foreground color and creates a histogram of all the colors available in this image. So when I say color, it is a misnomer because, like I said, we are dealing with the grayscale images. So even in the grayscale images, there are colors, right? So there will be very light gray and a very dark gray, and all the spectrum of grays are available even in the grayscale image. So when I say color, even though I am talking about a grayscale image, it applies to all the colors in the grayscale spectrum. So what Otsu's binarization does is it draws a histogram of all the colors available in the current image. Once it draws this histogram, what it does is it is a bimodal image. It assumes that the image is a bimodal image. So what do you mean by a bimodal image? That means there are two peaks in this histogram of the image. So we are assuming that the image will have two peaks, and then this peak will be split along with a certain axis. So what Otsu's binarization does is anything that is closer to one peak is given as white, and anything closer to the other peak is assigned a 0 value. Therefore, we are taking Otsu's binarization and using that to threshold our images. So coming to the next part, we can see that thresholded image when we run the demo. So let us find out actually the CV2 version that we will be using in order to avoid unpacking error. So what is unpacking error? So CV2 has different function signatures when it comes to find contours function depending on the version of OpenCV. Therefore, here we are checking if the version is 3 or 4, and then we are using the appropriate find contours function. So in our case, if you have followed our course from the beginning, you might have seen that our OpenCV version will be a 4. Therefore, we will be using this. So coming to the next part of the process, we have to actually extract the contours. So here we are extracting all the contours from 5 contours, and then we are finding the contour with the maximum area. So in the image we might find multiple foreground objects from the background, but out of all the foreground objects we are interested only in the maximum foreground object or the biggest foreground object. So in order to find the biggest foreground object, we will be calculating the area of each contour and finding the contour that has the maximum area. Now, how do we actually calculate the contour area is by this function called as contour area. So till here we have theoretically covered all the concepts that we have been exploring in the previous videos. Now let us go over them one by one, including the function signature and the values, in order to truly understand what the code is doing. So first we capture the webcam because it is 0, it is webcam. If you want to read a video file, then give the path to the video file here. Then we open the stream to the webcam, and then we actually read the frame. And then we draw a subset of the rectangle, that is x, y values, that is 100 to 300 and 100 to 300, and we are assuming that we are only going to do hand detection here. So converting to grayscale, we know that it is in CVT color, and we say that read it in CVT and convert it from BGR to gray. So using this option converts this image from BGR to gray. BGR is just another form of RGB. So here we are converting BGR to gray. Here we are applying a Gaussian blur of value 35, 35. That means we are taking a square of height 35 and width 35 and 35 pixels, and we are blurring them. So we use the Gaussian blur function on the gray frame of value which is 35, 35. And then we do the Otsu's binarization, where we say, okay, threshold this blurred image with the value 127. So all the pixel densities that are greater than 127 is assigned a value of 1, and all the pixels that are of lesser pixel density than 127 is assigned the value of 0. And here we are saying that use threshold binary inverse, that means we are using a binary threshold and we are using an Otsu binarization. Here I am sure we'll just show the thresholded image. Here we are checking the version of CV2, and here we are calling the find contours with a copy of the thresholded image, because we do not want to mess about with the original thresholded image. And then we are also passing other functions, other options to the same function. And then here what we are doing is we are finding the max of the contours, in which the max is calculated on the contour area. So here we are passing the key as the contour area. Alright, so now that we have got the final contour, that is the biggest contour, we are pretty sure that this biggest contour will have the hand region inside it. So next we will create a bounding rectangle around the contour. So what this does is we are just drawing a rectangle around this biggest contour that we found. So here we are saying cv2.rectangle of a cropped image and the x and y coordinates that we got from the bounding rectangle. And since this is BGR, we are saying 00255, so that means the rectangle will be in red color. Next we find the convex hull. So what we do in convex hull is we get the biggest convex hull from the contours. After that we actually draw the contours. So these two lines, we use the draw contours functionality in order to actually draw the contour around the hand. And in the next line here, what we do is we find the convex hull and we find the convexity defects, and then we draw the contours on these defects. So we apply the cosine rule to find the angle for all defects, that means fingers. So till now we detected the hand, and from this step onwards we will be detecting the fingers themselves. So in the next video I will be going over this next part of the code in which we are actually trying to track the fingers and recognize the gestures. Hello everyone and welcome to UpDegree. This is Sujay, your instructor for the OpenCV practical course. In the previous video, I explained to you about the code in order to extract the hand region. In this video, I will be going over the next part of the code in which we will be trying to extract the fingers themselves and track the gesture. So we already saw that we are extracting the convex hull, and then we find out the defectives in the convex hull. So the assumption here is that in the convex hull, any defect is because of the fingers. Therefore, if we find out what are the defects in the convexity, then we can find out where are the fingers present. So what we do is we get all the defects and then we count the number of defects using the for loop. So here we draw contours on all the contours, and then for each and every defect what we do is we find out the start, end and far regions of the defect. So then we find the length of all the sides of the triangle of this particular defect with this ABC. Now we find the cosine rule here in order to find out the angle. So any angle greater than 90 and highlight the rest with red dots. So we will be highlighting the fingertips with red dots. If the angle is less than 90, that means we are counting the number of defects and we draw a circle on that point. So the assumption here is that if the angle is lesser than 90 degrees, then that means it is a finger, because if we look at the fingers and the angle between them, there is no angle where a finger is greater than 90 degrees from each other. Therefore, we can safely assume that if we get an angle that is greater than 90 degrees, then that means it is not a finger point. So then we draw a line from the start to end, that is the convex points. So these convex points are the fingertips. So after this we define the actions that are required. So what we do is we count the number of fingers. Here we are counting the number of fingers to be 1, 2, 3, 4. So if we count this, we can safely say that we have detected one finger. So here we can change this text here saying that this means that we could detect one finger, and similarly if the count defect is 2, that means that we could detect 2 fingers, and if it is 3, it means that we could detect 3 fingers, and if it is 4, it means that we could detect 4 fingers. If it is anything greater than that, that means this means an entire hand. So what we are doing here is we are putting the text. So cv2.putText, we are putting the text at this coordinate in the image. So here we have different if conditions, where if the count defects is 1, that means it's 1 finger. If the count defects is 2, that means it's 2 fingers, and so on and so forth. Now coming to the last part, we will be showing the appropriate image, and all the images will be showed as a H stack, and then we will be showing it as contours. So here we are saying we will be taking in the input till we press an escape key. So 27 is the escape key. As soon as we press the escape key, then it means that we are done with the stream and that we can stop the stream. So this is the end of this video, and now that I have explained the entire code to you, in the next video we will be running this code and doing a demo of it. Thank you and see you in the next video. Hello everyone, welcome to UpDegree. This is Sujay, your instructor for the OpenCV practical course. In this video, we will be running the code that I explained in the previous video and finding out how it works. So you can save this code as gesture recognition.py in the same folder that we have been putting our codes. So here you can see in the terminal that so here I have saved it as gesture_recognition.py. So please activate your virtual environment like how I showed in the previous videos. So now let us actually go ahead and run the file. So I have run the file and I will be sharing my screen now in order to see how it looks like. So here you can see that this part is the subset of the entire video that we will be detecting the hand in, and as soon as I bring my hand in that, we can detect it. As you can see in the text behind that, we can see that it is a hand. So if you can see in the contours window, we can see the defects or the number of fingers that we are able to detect. If you can see the thresholded window, we can see that everything other than the hand is given as 0 and the hand is assigned the value of 1. So that is because of the odd-source binarization. And in the contours, the red is the biggest contour and the green lines are the ones that take the convex defects and count the number of fingers. Alright, so now that we have come to the end of the hand detection project, see you in the next video where I will be doing the next project. Thank you for watching.